Welcome back, everybody, to this second hour today. So let's see how far we go. So you remember, in order to get more bytes stored into our system, approach 1 is scaling up, down, up, down. Approach 2 is scaling out, in, out. So you just buy plenty of cheap machines. Approach 3, which is just as important as the other two, is to be smart and optimize. And that is the secret. If some of you try to create startups, who wants to create a startup? Some of you, right? When you start creating a startup, the question arises of how many machines do you need? Do you need laptops? Do you need to book resources in a data center? Talk about data centers soon. And what I noticed in the real world is that many startups actually do not need too many machines. Many startups can fit all the data in a single machine. But to do that, you have to think about the efficient use of the memory and structuring your data in such a way that it fits, maybe compress it, writing the computer code in such a way that it's efficient. And in fact, by just taking the time to sit, hire good software engineers and so on, you can save yourself a lot of money by still making it work on a single machine. That's approach number 3. And in fact, you should test this approach before you consider this approach and buying more machines, right? So this is just something that you need to be aware of. And there is this beautiful saying by Paul Barham, who said that you can only get a second computer once you know how to use the first one, right? So this is the word, excuse me, the word of warning before you scale out. All right, but having said that, now I'm going to focus on the scaling out, which is approach 2, which is the popular one in practice. Which brings us to data centers, because once we have realized that, yes?
So we were talking about the scaling just in terms of quantity and price. Wouldn't be like speed and time also be a variable in this decision?
Mm-hmm. Absolutely. So here we are just talking about the amount of storage, right? How do we pay to just have the amount of storage? But then, of course, comes also the question, how efficient is it going to run, to query the data, to let it flow around? So this is very important, and we'll actually spend several weeks on it. This is exactly the whole design idea behind MapReduce, behind Spark. I will explain to you how the creators of MapReduce and Spark designed it in such a way that it is very efficient in the use of resources, in the basically speed has to do with the bandwidth, the throughput versus latency. And so these architectures that we are going to learn in this course are very much designed like clockwork in the way that they work. And this is one of the topics of the course. And so I really take several weeks to go into all of this to explain everything. But you're absolutely correct. The speed, the bandwidth, the latency, all of that matters a lot as well in the design, right? So thank you very much for also pointing that out. All right. So now that we figured out that we can make it work with plenty of machines, we need a place to put these machines. These places are called data centers. Who has ever been in a data center? Some of you? You should. It's worth an experience. Sometimes we manage to optimize a field trip in the course where we did it actually last year with Big Data for Engineers in a data center in the north of Zurich. And so you can see for yourself the rooms that are basically filled with all of these machines to scale out. But I'm going to show you a virtual visit instead of actually going there. I'm just going to tell you what there is in a data center. So it's plenty of computers, obviously, just like your laptops right here. And typically in a data center, we have thousands or tens of thousands of machines that are connected together, of course, but tens of thousands. I put the higher limit of 100,000. I'm not aware of any cluster, which is another name for data center, like machines that are connected, that is more than 100,000. The reason has to do with the energy supply, electricity, and cooling. Because a data center like the ones that we have here in Zurich consume the energy of the airport of Zurich. to give you the impression, right, of the kind of energy that it consumes. So when you reach a number of machines like 100,000, it becomes very difficult to manage the electricity supply and the cooling down the whole thing. So this is why there is this hard limit. And then what you do is that you just open a second data center or a second cluster instead of continuing to put even more machines where you are, right? So tens of thousands of machines typically in a data center. Now you have to distinguish between companies like Amazon, Google, Microsoft, OVH Cloud, I think in Europe we also have, which provides the machines to the public. You can actually rent the virtual machines. With real estate companies for data centers, like Interaction, the one in the north of Zurich that we visited, is more a real estate provider. They provide the rooms with the electricity and the cooling, but not the machines. And then you as a customer rents the room, and then you can put your own machines in there, right? And then you benefit from the security. So there's it's an ecosystem with two levels, the real estate and then the providers. All right, so that's for the machines. Then the number of cores, you heard of 2 core, 4 core, 16 cores on the same machine. Nowadays, plenty of laptops probably have 10 or even 16 cores. In a data center, in a single machine, you can even have 64 or even more than 100 cores, right? So the machines are a bit more scale up a bit more than the laptop, so it's possible to have a bit more, right? I just rounded it up, but think maybe 128 because we love powers of 2 when we use cores. All right, I'm just giving you orders of magnitude here. Then the local storage, typically it's plenty of disks that you put in the machines. Here I told you the largest drive we have today is 100 terabytes. Right, and it keeps growing. Actually, I have to update these once in a while. So that's for a single disk. But of course, in a data center, you're going to have thousands of disks, right? So you can imagine the size that you can store in there. Then we have the RAM. RAM is for random access memory. That's the working memory. That's basically what allows the computer to compute in real time. But if you shut it down, it's gone, right? So that's the difference with the disk. That's the working memory. But it has the advantage of being much faster than the disk. And so here, on your laptop, you have 16 gigabytes, maybe many of you. Who has 16? 24? 32? 64? 128. Nobody has 128. On Zoom, also not 128? Yeah. You have 128? Oh, wow, okay. Memory, the amount of working memory. Yeah, no, 128 is a lot. In a data center, you can absolutely have 128 gigabytes, right? In fact, you can even have terabytes of working memory. And there is a trend of database systems where the data all fits in memory. You don't even bother reading it from the disk. You just put everything in the memory, and that's it. And you keep it running. All right, so I even found some with 24 terabytes. Of working, that's not the disk, that's really the working memory has 24 terabytes in a data center, not on a laptop. Then we have the network. So the network can go all the way to hundreds of gigabits per second. They count in bits instead of bytes because on the network, it's really the transmissions of ones and zeros that we're interested in on a line. But basically, it keeps growing up as well. Here, 1 gigabit, that's typically what you have at home, right? Die schnellste Schweiz der Welt, there were funny ads at some point. So 1 gigabit is what you have at home. And in a data center, it's a bit the question you asked also earlier. You can have tens or thousands of gigabits per second between the machines. All right, so that's for the machines to communicate. And of course, during the course, I will explain to you how they communicate, how we actually make them communicate to make them do what we want them to do for the data storage and querying. Now, I told you we have thousands of machines that are a bit like your laptops, but these are not laptops. So do not imagine a data center with thousands of laptops like this. Instead, what we have are towers like this that you see on the screen that are called racks. And these racks are just piles of computers. So this is a single one. That's what it looks like. One that would be an equivalent of one machine. It's all standardized, so the heights of these are standardized, typically 1, 2, 3, 4 rack units. RU is rack units. And so it's like a Lego game, right? Then you buy these towers, and then it's all made up in a certain way that you can clip the machines in there. You call them nodes, the machine. So this is why instead of calling it machine or computer or server, you might also hear the word node, right? Because if you visualize the topology of the network as a graph, then a machine is a node in the network. Now, some of them might be machines like this. You see the fans in the middle to cool down the CPU. But in fact, you might have plenty of machines. You might also have some nodes here that are just disks. You just put 10 or 20 disks on one level, and you just connect them to the rest of the rack. You might also have a layer here just for the network switches, and then all of the machines in here connect to the network switch in here, and then it goes and connects with other racks, right? So it's really like a Lego game that you assemble these towers in this way. So servers, machines, disks, network switches, routers, and so on, right? You're going to have plenty of these towers, plenty of these racks in the same room, maybe 10 or 20 of them in a room. And then you imagine all the electricity that comes to the room and the cooling that you need and the fire systems, extinguishers, and so on. So you need a lot of infrastructure to make it work. And this is why here you see some representation of what it looks like. All of that in military-grade security, right? It took us typically half an hour for everybody to enter the building when we go there, because they screen, and then there's all kinds of doors that you need to pass. So everything is very highly protected. All right. So that's what we have in a data center. So that's the hardware, the physical level. Now we need to use it to store things. One of the use cases that I can give you for storing stuff is Netflix or whatever else, right? Disney Plus, HBO, and so on. So why is that one of the users of this? Because they need to store all of the movies and the shows somewhere so that they can stream them through the internet. And so they basically need a place where they can cut the movies into chunks of a few seconds. And then when you stream, what it actually means is that you download your chunks, and the computer just manages that in the background. And then it shows you the whole show because it keeps downloading the chunks in real time. It can even adapt the resolution, because you might store these chunks as files with a higher or lower resolution. It automatically adapts. So this is what we call streaming. But all of these chunks, these little files that contain a few seconds of a show or of a movie, they need to go somewhere. And this somewhere is as cloud storage. Amazon offers that. Microsoft offers that as Azure storage. Google offers that, and so on. And typically, a service like Netflix or others are connected to multiple of these cloud storages. Maybe they are going to both have Google and Amazon. I don't know actually what, but let's say Google and Amazon, or Azure and Amazon, for example. So this is one of the use cases. Another use case is, for example, who has, I don't know, iCloud, stores data in the Apple cloud, right? If you have a firewall on your machine, you might notice that it tries to connect to S3 or to Google or to Azure. This is because in the background, this is what we have. This is the cloud storage that it is actually using. And probably it also has, they also have their own servers, but it's all the architecture of the internet on which all of that is actually working. So when I talk to you about S3, of course, you will store data in there like XML, JSON, but this is where your pictures are. This is where the TV shows that you watch on Netflix are all stored. This is that kind of storage. And so for that kind of storage, we need some worldwide system that allows you to store billions or trillions of files that we call objects. That can be anything: video, audio, data sets, anything, files, generic files. And it needs to scale for the entire planet. So we have a few tricks to make it work. The high level, I'm going to do that almost every week. There's the logical level, and then there's the implementation. Well, I'm going to break the, not give you any cliffhanger. The implementation of S3, we don't know because they don't communicate about it. So just so that is clear, I can give you the logical model. However, Azure talks about it. So here they wrote a paper that I put in the lecture material. So in this paper, Azure Blob Storage explains how they actually implemented it. It's likely that there's overlap with the way that S3 implements it as well, but we can only. So what happens is that logically, it's very simple. You can have buckets in which you can store your data, buckets. And each bucket has a bucket ID. It's a name, right? That's how it's called, bucket ID. Inside the bucket, you can put objects. And an object within a bucket is identified with an object ID. Every object that you see here is one file. Right? Object is just a name for file in cloud storage. So maybe here this is a picture, and this one is a JSON file, and this one is a chunk of a Netflix video, and so on. Right? So these are called objects. So concretely, if you want to retrieve one of these objects, you need a bucket ID and you need an object ID. And if you give the bucket ID and the object ID, you can get it. You can also write it to the cloud storage. Of course, you need clearance, right? Not everybody can download everything. You still need maybe a username, a password, or an authentication token. Some of them might be public because they are accessible to everybody. For example, some people use this for websites, in which case it's open to everybody. So anybody can download all the objects and view the website, right? So you see, very simple. Bucket ID plus object ID gives you an object. But there is a size, a limit on the objects that we can have in there, which is at most 5 terabytes for one object. The order of magnitude is interesting because 5 terabytes fits on a single drive, right? So that might be a hint that maybe these objects are stored in a single chunk on the drives, right? But yes, that's the maximum size. And if you have an account with Amazon, you can have up to 100 buckets. If you need more, you need to file a request with them because obviously, since it's a worldwide system, they don't want people to create tens of thousands of buckets each, and then it's a huge mess in the naming system, right? So this is why they limit it a little bit, but you can create 100. Typically, imagine that if you want to host a website, you need 1 bucket for that. If you want to host maybe a few data sets, you create 1 bucket for that, and you put it all in there. Okay, so at most 100 buckets. 1 object is at most 5 terabytes. There is no limit to the number of objects in a bucket, at least not that I know. All right, so far so good. Any questions? Okay. Now I'm going to go to the legalese, the lawyer hat. When a company like Video on Demand wants to store its data in some cloud service, they obviously want guarantees, right? Because they have customers that pay for their subscriptions, so they want guarantees on the availability of the data, the fact that people can actually connect and download the chunks of the TV show and so on, and also that the data is not lost, right? Because if they store the chunks and then the data disappears, then that causes a disruption to the service. For this reason, there's service level agreements, which are contracts between the cloud provider and the users of the cloud provider. And these contracts have a lot of numbers that look like this, with plenty of nines. It's scary at first, but if you think of it, it's not that scary. For example, here, I'm saying we have a durability guarantee of 99.999999999%. And what that means is that every year, if you store 100 billion objects, that's already a lot of objects, right? But imagine you store 100 billion objects, on average, 1 of them is going to be lost every year, right? So that's the guarantee. They guarantee that you're going to lose at most 1 of these 100 billion objects. Then it's up to you to decide if that's acceptable or not, right? If you're a video on demand provider, it's acceptable, right? Worst case, you just upload it again and that's it, right? And maybe 1 customer will at some point have been affected by it. So it's up to you to decide, right? But this is an example of durability. We also like to use the nines not for durability, but for availability. Availability is a guarantee that the system is available, obviously. But what it means concretely is 99.99%. It means that in a year, maybe for 1 hour, the system is going to be unavailable. Yes? Yes, so there's two aspects here. There is the implementation aspects, like how do you implement it in such a way that it guarantees that? And then there is the lawyer aspect, the lawyer that draft the contracts and say, okay, we promise you that. In terms of implementation, we'll see during the semester that one way to avoid data loss is replication. If you store it multiple times on multiple machines, then the risk that you lose all of them is much smaller than if you only have one replica. So this is one way. We don't know, again, how S3 is implemented, but I highly believe that if they make that kind of guarantees, they probably replicate. Because with a single machine, I don't think you achieve that kind of guarantee, right? So replication is one way. And then in terms of the guarantee, it's an estimate. You probably need to organize a meeting with the engineers and the lawyers that basically they come up with a guarantee that they think, okay, now it's reasonable to give that guarantee, right? Does it make sense? Yeah. There is no way for me as a customer to actually know that this is true that thing, because I cannot link up with all other customers to check if that's actually. Yep. So here you're already entering, we're already in a court, fighting about the thing. And basically, this is how it happens in real life, right? If a customer is unhappy, they are going to take it to court. But basically, this guarantee is an overall guarantee of the entire system, right? So if you have 100, trillion, then in a year, you're going to have 1,000 that are going to be lost. So now, there's of course statistical fluctuations, right? As a customer, you might be unlucky and then you get two lost and maybe other customers did not lose anything at all, right? Then I'm not a lawyer. I don't know the specifics of the contracts and so on, but I assume that if somebody would actually make a claim or whatever, then they probably have ways to figure out with precedence cases and so on how it's actually handled. Maybe, I don't know, I'm just guessing because I'm not a lawyer. You could do an investigation on the whole systems and see how many were lost as an aggregate for all customers or and so on, right? But here we're really already entering the details of it. I would say that you should take that, let's say, as a probability. Like every year you toss a coin, and this is the probability that you use that you lose an object. I would say, right? All right. Very good. But of course, these are interesting questions, right? And you see that's interdisciplinary because you get a lot of people of different professions that sit together and discuss these things. All right. Now we have availability. That's how much of the time is it down? Down means you try to connect to watch a show and you get an error because it's unavailable. And so you can have these kind of promises that say, okay, we promise it's going to be available 99.99% of the time, which means over a year, it's not more than an hour that it's unavailable as an aggregate over the whole year. So you see, people love these nines, right? Nines all over the place. I gave you a few examples here, right? So if you say, I have a 99% availability, that's 4 days every year. If you have 99.99999%, then it's 4 seconds every year, right? So this is then up to the customer to decide what is acceptable to them. So typically a cloud provider might give different guarantees for different prices, right? You pay a higher price if you want a better guarantee, and you can pay less of a price if you need less of a guarantee. A concrete example, you might have backups, and maybe you don't care if it's unavailable for 4 days, right? If you need to wait for 4 days until you get your backups, maybe this is fine. Then you take the cheaper version with a bit less availability, and you can live with it. And some other people might have super critical system, like, I don't know, an autonomous driving system with plenty of cars connected. Probably you want a very, very super high availability, like 4 seconds a year maximum in aggregate. SLA is service level agreements, right? That's just what I said earlier, SLA. Another way to use the nines is the response time. Now, for the response time, we don't like to give averages. Rather, we like to give an upper bound that is guaranteed with a certain probability. For example, we like to say, we promise a response time that is less than 10 milliseconds in 99.9% of the cases. That's an example. These numbers are just made up to show you how it works, right? These are not the S3 numbers, but basically, this is to show you how it can look like in a service level agreement, right? And then once in 1,000 cases, you might have a longer response time, right? And but most of the cases, it's less than 10 milliseconds. All right, yes? Yes, absolutely. So this is, I'm going to repeat for the people on Zoom. The idea is that in order to provide availability, you need some redundancy. You're going to run the service from multiple machines. You probably, I'm also going to talk about it, want to spread your machines over the planet a little bit. Because there could be an earthquake, there could be a tsunami, right? And so if you want to ensure that it remains available, then you put it at different places to duplicate further, right? So this is exactly how it works, absolutely. There was at some point a fire in Eastern France, I think, in a data center, and actually they didn't do any backups, and that actually had consequences for the companies that had their data in there. So availability and redundancy is actually very important. All right. Let me continue with the CAP theorem. You remember ACID? I told you about ACID for the traditional database management systems, where you have atomicity, consistency, isolation, and durability, ACID. When companies like Amazon, Google, and so on noticed that they needed to scale up their systems, they also noticed that they couldn't do it in an ACID fashion. It just, at least at the time, wasn't possible. So what happens is that when you go at scale and have 1 billion or 1 trillion objects offered in a storage like that, you make a few compromises, right? You just say, okay, we're not going to offer the full ACID compliance. We are going to offer a bit less than that. And some people have even researched what's possible and what's not possible. And when you want to say what's possible and what's not possible, a very popular of doing that is an impossibility triangle. You basically give 3 things and you cannot have all 3 at the same time. You can have any 2, but not all 3 at the same time. The CAP theorem is such an impossibility triangle, and C, A, and P are the three vertices of the triangle. And they mean this: consistency, availability, and partition tolerance. You cannot have all the 3 at the same time. And I'm going to explain what they actually mean. Consistency, it's not the same as in ACID. Be careful about that. This doesn't mean that the data is consistent in the sense that, for example, a balance is always positive on a bank account or something. What we mean here, in the case of the CAP theorem, is that since the data is replicated and there is some redundancy to ensure availability, there might be the risk that different machines give you different results, right? You might have copies of the same data on different machines. What if they do not give you the same data for the same bucket ID and object ID, right? You do not want that, or maybe you do, but generally that's something undesirable. So if you want to make sure that at any time, if you ask plenty of machines for the same data, they should give you the same data, right? So this is called atomic consistency. All nodes see and deliver the same data at the same time. That's the C. Now we have the A for availability. Availability is what I already told you with the nines, right? It's the idea that the system is available and that you can always use it and make a request and get a response. Unavailable means that you get a message that says, not available right now, please try again later, right? That's an unavailability message. But available means that you can connect to the system at all times and get an answer. At all times, probably meaning 99.99999 with a lot of nines, right? And the third one is partition tolerance. And in order to explain that, I have here a small animation. I told you that the computers in a data center are called nodes, right? Well, here it's literally nodes that I put them as a graph. So every node in here of that graph is a computer, and they are connected with the network cables, technically. And of course, they exchange data. For example, when you replicate data between computers, they will send the data over the network cables in order to replicate it somewhere else, right? So maybe somebody is going to update the data at some place, and then that update has to propagate over the network cables to all of the nodes, right? One example of that is Bitcoin, the blockchain. So whenever you update the blockchain, it needs to propagate to all of the nodes behind the blockchain network. So it propagates like this, and then more and more nodes are going to have these new versions. But it takes time. It's not instant, right? It's not instant. It takes time to propagate, and then at some point, they will all have the modification. But the problem, and then it's just like in a Netflix series, we have some event in here, an earthquake or whatever, that breaks the network, and maybe a network cable is failing, and then the propagation cannot go all the way to the other side that is disconnected. What you have here is called a network partition. A network partition means that all of the nodes are no longer in a single connected component. That's what the graph theory people would say. It's a connected component. Now you have more than one connected component in there. So you can no longer propagate the updates all the way. What this means concretely is that when there is a network partition like this, exactly one of three things is going to happen. And that gives you the three possibilities for the impossibility triangle. Possibility number one, we have a network partition and the entire system crashes in a way that is beyond fixing. That's over, bam. That's possibility number one. In that case, we say the system is not partition tolerant. There was a network partition, it's over, right? That's possibility number one. Possibility number two is the system becomes unavailable. It's still online, it still works, but whenever people connect, it sends nice messages that says, please come back later, we are currently unavailable. It's not crashing because you still deliver these nice messages that tell you the users, please come back later. So in that case, we say that the system is consistent because what's happening is that it's not available in the time that it's inconsistent. Right here, you have an inconsistency between the left and the right. But since the system is on pause, then the users don't notice that it's inconsistent. Then at some point, I'll go to your question. When the partition is fixed, then it will propagate again. And once it has propagated, then it's available again, right? So this is the second possibility. And then it's consistent at all times because whenever it's available, then it just gives the same data everywhere. Yes? Absolutely. That's possibility number three. That's the third way you can handle it, is by saying, we continue to serve our clients, we continue to be available, but we live with the fact that the people connected to the left might see something different than the people connected to the right. Right? Yes, so it might be that it's possible. I will continue the discussion offline. What I should say is that the CAP theorem is not fully formalized. It can be interpreted in different ways, and you know, with the definition. So it's absolutely true that you can make arguments in different way. I'm very interested in hearing how you think about it. It's true that if you change the definition of availability and are a bit more lenient, then you get different, probably different tastes of the system. I might be a bit simplifying here to get the point of CAP and only two among three, right? Please send me an email with exactly. Yep. All right. So possibility number one is you crash. Possibility number two is you become unavailable and then you available again when it's connected again. Possibility number three is you continue to be available, but you're not consistent, right? This is also called eventual consistency. All right. And there is even a generalization of the theorem that's called the Pakelk theorem, which basically is all about, in the case of a partition, you choose between consistency or availability or crashing. And in the normal case, when there is no partition, then either you are consistent or you are low latency. And then you get all of these possibilities in there, right? Any questions? All right. And again, we'll continue offline if you send me an email to discuss that. Yeah, very interested if there's another view. All right. So this is the CAP theorem. I still have a few minutes, so now I'll tell you about REST APIs. You know the web, right? www and HTTP. It was invented in 1989 by Tim Berners-Lee, who is right here. And this is the system that allows you with a computer and a browser to connect and fetch web pages or pictures or all kinds of files over the internet. This is human to machine, right? You're in front of your computer, you connect, and then you get a page. REST can be seen as an extension of that machine to machine. Instead of being a human that types things in a browser, it's a computer that connects to a server like that. And this is called a REST API. It was the PhD that was written on it that uses HTTP for actually programming. And so basically, when you have a database system or provide it as a service, you can use the shell to connect to it. You can use a host programming language with some driver to connect to it. You can use a fancy notebook, or you can use a REST API. And in fact, you can even build the others on top of a REST API, right? So that's a good foundation for a system. So now, what is a REST API made of? The paradigm is based on resources and methods. A resource is something that is part of your model. Could be a picture, could be a file, but it could also be a light bulb, you know, with the Internet of Things or whatever you want. It's a resource. A resource can be identified with the universal resource identifier, URI, right? It looks like this. Now, this kind of URI turns out to be an HTTP URI, but these are not the only ones, right? But it looks like this. You have a scheme here, HTTP, Hypertext Transfer Protocol. Another one is mail-to or FTP or HDFS, other schemes. Then you have an authority, that's the domain that you have in here. Then you have a path, all the slashes. Then you have a query, that's when you have the question mark. So typically that's when you fill a form and it's transmitted, can be transmitted in this way. Then you have a fragment, and the fragment is going to, that's the sort of thing, for example, on Wikipedia, it brings you directly to a subsection of the page. So that would be called a fragment, right? So it looks like this: scheme, authority, path, query, fragment. So that's called the URI. There used to be also URL, Universal Resource Locator, URN, Universal Resource Name, but these are deprecated now, and we just say URI. In fact, even URI is supposed to be deprecated. We should say IRI, International Resource Identifier, but I'm not aware of anybody who actually didn't really catch up. So not many people say IRI. I think URI is probably the word that most people use today. And so when we have S3, we are also going to be using these URIs to identify buckets and to identify objects. So you see, for example, the URI of a bucket would be the name of the bucket, for example, .s3.eu-west1, maybe in Frankfurt, I don't know, .amazonaws.com. That's a bucket ID, a bucket URI. And then at the bottom, you have an object identifier with a URI that has the bucket name in orange on the left and the object ID on the right? And that gives you an object. Okay, so that is a URI that identifies a resource. In addition to these resource identifiers, you have methods that are actually verbs. There's several of them, but I'm just going to focus on 4: get, put, delete, post. And the idea is that whenever you use a REST API or the HTTP protocol, you basically give a method and a URI. For example, get the contents of that object, right? And then you get a response with some status code. Who knows the 404 not found? You all saw it, right? So 404 is the status code, and there's plenty of other status codes like this. Now that's for the geeks in us. So this is what it actually looks like whenever you connect to a website behind the scenes. Your computer sends what you see above the arrow, and the website replies with something that looks like what's below, right? So this is the actual thing that is going on with your browser. So now the methods get is just getting a resource. More exactly, it's getting a representation of the resource. Could be text, XML, JSON, CSV, and so on. If it's a light bulb, obviously it's not going to return the light bulb over the internet, but maybe you're going to get some information about the light bulb, like is it on, is it off, and so on. So that's get. Get is not supposed to modify anything. The only thing it does is it retrieves information and that's it, right? There might still be some logging that it logs that you attempted to get it, but this is not really considered a side effect in terms of the API. As for post, delete, put, I'm keeping them for next week, and then I'll take it from there, right? So thank you, everybody, for listening today. Next week, I'll finish this, and then we'll start talking about HDFS, which is the Hadoop distributed file system. Thank you very much. Thank you, Ludovica, for the moderation, and enjoy the exercise sessions, and see you next week.